Now, this is our second lecture of organic chemistry. In previous lecture, we have studied about what is meant by hydrocarbon, and up till now we come here to the concept of aromatic hydrocarbon. Now, what is meant by aromatic hydrocarbon? I have already told you that from where this aromatic word arises. Now, aromatic word arises from the Greek word aroma, meaning smelling. It means each and every aromatic hydrocarbon has its own odor. Now, what is meant by aromatic hydrocarbon? Now, aromatic hydrocarbons are those compounds which contains carbon and hydrogen, only and satisfy the Haeckel's rule of aromaticity. Haeckel's rule of aromaticity. Those compounds which contains carbon and hydrogen only and satisfy the Haeckel's rule of aromaticity are considered as aromatic hydrocarbon. Now, we know that the first member of aromatic hydrocarbon is discovered by Kekulé in 1865, named as benzene. Which has a structure like this. Now, this benzene atom has 3 pi bonds. This benzene atom has 3 pi bond. It means it has total 6 pi electrons. 6 pi electrons. Now, these 6 pi electrons circulate above the plane of benzene and below the plane like this. Due to the circulation of pi electrons, above the plane of benzene ring and below the plane, the benzene ring becomes nucleophilic in nature. It becomes nucleophilic in nature. That's why any aromatic hydrocarbon undergoes electrophilic substitution reaction. Due to its nucleophilic tendency here, benzene also undergoes aromatic electrophilic substitution reaction. Now, preparations of aromatic hydrocarbons. Now we know that the preparation of one functional group is the chemical reaction of another functional group. Now, we have to see that the preparations of aromatic hydrocarbon. Now, in our syllabus, we included benzene molecule only. Now, preparations of benzene. There are 4 preparations of benzene included in our syllabus. The first one, reduction of phenol. Second one is decarboxylation of sodium salt of benzoic acid. Second one is decarboxylation. of sodium salt of benzoic acid. Third one is from acetylene. Third one is from acetylene. And the last one, that is from benzene, sulfonic acid. Now there are 4 preparations. Out of these 4 we have to see reduction of phenol firstly. Now we know that when there exists a word reduction, where there comes a word reduction, it means we have to reduce phenol. For that reduction we have to use zinc dust. Now when phenol is treated with, when phenol is passed over a heated zinc dust, we will obtain benzene as a product with the formation of zinc oxide. Now in this reaction, zinc dust acts as a reducing agent. It acts as a reducing agent. Now we know that the reducing agent has a tendency to reduces others and itself gets oxidized. Now we have to move towards the reaction happens in this head. Now we know that this phenol, when passed over zinc oxide, zinc dust, this zinc dust reduces the phenol molecule to form a benzene with the formation of zinc oxide. In this case, initially zinc is in its zero oxidation state, which converts to the +2 oxidation state. It means here zinc gets oxidized, whereas this phenol ring gets reduced. This is the first preparation of benzene. Now we have to prepare benzene by another way, that is from decarboxylation of sodium salt of benzoic acid. Now we all know that calcium oxide and sodium hydroxide, that is soda lime, are the decarboxylating agents. Whenever we saw COOH or COONA functional group in any compound, by using this calcium oxide and sodium hydroxide, we have to decarboxylate that molecule. Now here the main reaction is like drawn on the blackboard. When sodium salt of benzoic acid is treated with calcium oxide and sodium hydroxide, that is soda lime. These two groups decarboxylate the COONA group to form benzene with the formation of sodium carbonate. Calcium oxide and NaOH is generally used to remove CO2 molecule from sodium salt of fatty acids and from carboxylic acids. Now, third reaction of this chapter is preparation of benzene from acetylene. Now, it is this cyclic polymerization reaction in which red iron tube is used in this reaction. We have to pass the 3 moles of acetylene molecules through red hot iron tube at high temperature, that is here near about 873 Kelvin. Now this acetylene molecule undergoes cyclic polymerization to form benzene as a product. The structurally reaction is shown as now these 3 molecules of acetylene is treated with what? Is passed through red hot iron tube at about 873 Kelvin. It forms benzene as a product. Now, the last preparation of benzene, but not the least important, from benzene sulfonic acid. From benzene sulfonic acid. In this reaction, benzene sulfonic acid is passed over hot steam. It means this reaction, or it means benzene sulfonic acid is hydrolyzed by steam to form benzene as a product. In this case, this benzene sulfonic acid is hydrolyzed by hot steam to form benzene as a product. The reaction is diagrammatically shown as this is the product of this reaction. Now we have seen all four preparations of benzene. Now I have already taught you that benzene is nucleophilic in nature. While proceeding towards the chemical reactions of benzene, we have to further study why benzene is nucleophilic in nature. Up till now, we have studied what is meant by aromatic hydrocarbon and preparations of aromatic hydrocarbon regarding the molecule of benzene. Now we have to see the chemical reactions of benzene. For that purpose, firstly, we have to see that this benzene molecule has 3 pi bonds. It means it has 6 pi electrons. These 6 pi electrons are in circulation. These 6 pi electrons are in circulation above the plane and below the plane of benzene. These 6 pi electrons are above the plane and below the plane of benzene. Due to circulation of these 3 pi bonds, that is 6 pi electrons, benzene molecule acts as a nucleophile. It acts as a nucleophile. Now, therefore, this benzene molecule or any aromatic molecule undergoes aromatic electrophilic substitution reaction. Aromatic electrophilic substitution reaction. Now, the general reaction of aromatic electrophilic substitution is this benzene molecule is treated with electrophile. It gives electrophilic substituted product. In this case, electrophile replaces one of the hydrogen atom from benzene. This electrophile replaces one of the hydrogen atom from benzene to give electrophilic substituted benzene as a product. The mechanism of this reaction is as follows. Now, mechanism of attack of electrophile. Mechanism of attack of electrophile on benzene ring. In first step, this benzene molecule attacks on the incoming electrophile. In this way, we all know that this is arrow pushing concept. Now, this arrow indicates that the electrons moves from this tail to the head. Now, it results into the formation of sigma complex. It results into the formation of sigma complex. It is also called as a uranium ion. It is also called as a uranium ion. Now, this uranium ion is a resonance stabilized species, which is shown as follows. This pi bond delocalizes with this positive charge to give the second resonating structure of aromatic hydrocarbon. Further, this positive charge delocalizes with the pi bond to give the third resonating structure. This is the resonating structure of uranium ion or sigma complex. Okay, now this uranium ion or resonating of uranium ion is written as a resonance hybrid as follows. This is the resonance hybrid of this uranium ion. Now, in final step, the attack of nucleophile takes place on. Now, in final step, the attack of nucleophile takes place on this proton, and the electrons present in this bond restore between the bond on which between the carbon atom on which electrophile is present and the positively charged carbon atom to give electrophilic substituted benzene ring. In each and every case, this is the mechanism of our chemical reactions of benzene. Now, one by one, we will see which type of chemical reactions happens on the benzene molecule. Now, the first reaction is nitration. In nitration, when it occurs on the benzene ring, NO2 group replaces one of the hydrogen atom present on the benzene ring by NO2 group. Now, this nitration reaction is carried out at 40 degrees Celsius. For that purpose, we use nitrating mixture. That nitrating mixture undergoes a reaction. It is a mixture of concentrated H2SO4 plus concentrated HNO3. Both these react to give HSO4 minus along with acid H3O positive plus NO2 positive, that is nitronium ion. That is nitronium ion. Now, this nitronium ion is used for nitration of benzene. This will be the electrophile generated from nitrating mixture. That generated electrophile, that is nitronium ion, will be used for nitration of benzene. So the reaction of benzene is shown as, now this benzene ring is treated with concentrated H2SO4 plus concentrated HNO3 at 40 degrees Celsius to give what? To give nitrobenzene as a product, to give nitrobenzene as a product. This is the first reaction of chemical reactions of benzene. Now the second reaction, is sulfonation. In sulfonation, we have to use fuming sulfuric acid or oleum. Oleum means concentrated H2SO4 contains dissolved SO3. Now when benzene molecule is treated with oleum, that is fuming concentrated H2SO4 at 373 Kelvin, it gives benzene sulfonic acid. As a product. This is the second reaction, sulfonation. Now moving forward to our third reaction, that is halogenation. For halogenation, we have to keep one thing in our mind, that each and every halogenation on aromatic ring, here we use benzene, that's why on benzene ring is carried out by using Lewis acid. It can be carried out by using Lewis acid. Generally for that purpose we use Lewis acid like FeX3 or ALX3. If we have to carry out chlorination, then we have to use FeCl3 or AlCl3. Instead of chlorination, if we use bromination, then we have to use Lewis acid such as FeBr3 and FeAlBr3. Okay. Now when benzene molecule is treated with Lewis acid, or when chlorination of benzene is carried out, then we have to use anhydrous AlCl3. It will give chlorobenzene as a product. Instead of this anhydrous AlCl3, if we use anhydrous FeCl3, then also we will obtain what? This chlorobenzene as a product. Now we know that here AlCl3 acts as a Lewis acid. That means it has a vacant orbital. Now that vacant orbital acquires firstly the electrons from this chlorine bond, chlorine molecule. Okay, now next reaction is Friedel-Crafts alkylation. Friedel-Crafts alkylation. In Friedel-Crafts alkylation, we also use Lewis acid. In this case, this Lewis acid acts as a catalyst and along with that, it also helps to generate electrophile. Now, Friedel-Crafts alkylation or Friedel-Crafts acylation, both these reactions generally carried out in anhydrous condition. Now, anhydrous means lack of water. Generally, Friedel-Crafts alkylation and Friedel-Crafts acylation are carried out in anhydrous condition. It means in absence of water. Due to, if we use hydrous condition, the reaction will be exothermic. There is a chance of blast in that case. So we carried out this Friedel-Crafts alkylation or Friedel-Crafts acylation in dry condition. This reaction totally depends upon the stability of carbocation. Now, those molecules which form a stable carbocation easily undergoes Friedel-Crafts acylation. Now, when this benzene molecule is treated with any alkyl halide, that is RX, it gives, in presence of anhydrous AlCl3, it gives alkyl benzene as a product. It gives alkyl benzene as a product. Instead of, we already see that the reaction or the alkyl halide used in this reaction totally depends upon the stability of this alkyl substituent, and we all know that we have to use such alkyl substituent which has greater stability on the basis of its carbocation. That's why we use tertiary carbocation containing alkyl halide followed by secondary and followed by primary, which generates tertiary carbocation preferentially used in this Friedel-Crafts acylation. Now, for example, when this molecule is treated with, when benzene is treated with tertiary butyl chloride in presence of anhydrous AlCl3. In presence of anhydrous AlCl3, it will use tertiary butyl benzene as a product. It will give tertiary butyl benzene as a product. Now, the next reaction of this chapter is Friedel-Crafts acylation. That is Friedel-Crafts acylation. This is also very much similar to Friedel-Crafts alkylation. In Friedel-Crafts alkylation, we use alkyl halide. In this case, we have to use acetic anhydride or acyl halide. For example, if we use acyl chloride, or if we use acetic anhydride, both these molecules generate acylium ion, which is also a resonance stabilized species and acts as a electrophile. It is also a resonance stabilized species and acts as a electrophile in Friedel-Crafts acylation. This reaction is also carried out in presence of anhydrous AlCl3 or Lewis acid. Here also Lewis acid acts as a catalyst and as well as it helps to generate these electrophiles. Now Friedel-Crafts acylation. When benzene is treated with acyl chloride in presence of anhydrous AlCl3, we will obtain acetophenone as a product. Acetophenone as a product. Now, these are the 5 reactions. Now, next reaction of this topic is the oxidation of side chain. Is the oxidation of side chain. In this oxidation, we have to use acidic camenophore. Now this acidic camenophore is the strong oxidizing agent. It is the strong oxidizing agent which oxidizes almost all side chain present on the aromatic ring to the COOH group, that is carboxylic group. Now, when this benzene ring containing CH3 is treated with a strong oxidizing agent, acidic camenophore or KMnO4 in acidic condition, we will obtain benzoic acid as a product. We will obtain benzoic acid as a product. If there exists a multiple alkyl group present on the aromatic ring, then this KMnO4, as being the strong oxidizing agent in acidic condition, oxidizes almost all alkyl groups present on the aromatic ring to carboxylic group. For example, if there exist two methyl groups, or instead of these two methyl group, if I use a methyl group and one ethyl group, when this ethyl methyl benzene is treated with KMnO4, which is a strong oxidizing agent in presence of acidic condition, it will oxidizes both this side chain to the carboxylic group. Means this CH3 will convert into COOH, whereas this CH2CH3 is also converted to COOH. Instead of multiple alkyl groups, if there is a side ring, instead of multiple alkyl groups, if there is a cyclic ring present on any aromatic ring, and we want to oxidize that cyclic saturated ring, we also use KMnO4 in acidic condition. It will also oxidizes this ring to COOH group. Now, this is all about the chemical reactions of benzene. Okay, thank you.